Hello everyone and welcome back. We're going to be doing some more PLC IOSIM challenges today. So far we've worked our way all the way down to the Stacklight 2, which we finished in the last video. And yeah, go check out PLC IOSIM. The creators have made 2 more levels for us, 25 and 26. We're going to see, starting on manual mixing tank, how many we can get done in this video. Let's go. Design a program to control a mixing tank manually. Pressing push button number 1 should energize solenoids valve 1 and 2 to begin filling the tank until float switch high is operated. Okay, let's do that. So we have push button 1. You're going to want that to latch 2 things. First, you're going to want it to latch the valve 1 coil on, and same thing for number 2. And to unlatch these filling tabs, you're going to want to use either one of 2 things. You can use the stop button. We'll use normally closed because the stop button here is normally closed, meaning this will actually be normally open until you click stop. The other way that we can unlatch these 2 valves is by reaching the high level limit switch, which will energize once we reach the top, and then causing this contact to close. So this will be the high switch, and we'll just make either of those things unlatch both of the valves, valve 1 and 2. That should work. PB2 should energize solenoid discharge to empty the tank until the low float switch is unoperated. So push button number 2, our second input, should energize solenoid discharge. We're going to use a latch function again. And to unlatch, we have 2 options again. We can use our stop, same as before, or we can use our low level limit switch. So as the water is going down, the switch will actually be closed because it's a float switch and the level is above it. So because this switch will be closed, whatever contact we put here will be negated, i.e. energized. So we'll make a normally closed contact here. That way, when this float switch opens, when the level gets low, this contact will de-energize and become closed. So that will be our low level. And we will use either of those 2 things to unlatch the discharge valve solenoid. So let us see if this is going to work. I'll just quickly try filling the tank. You can see we're going up, up. When we hit the high switch, this should close. And boom. Yep, it stopped filling. That's good. We'll do the discharge. When we hit the bottom, this switch should trigger, and this discharge should turn off. And we should also be able to click stop to just stop the process. So, boom. So that's good. Now all we have to do is add the mixer. So the mixer should turn on if the level is above the medium level float switch, and it should turn off if it's below there. And you should also be able to turn off the mixer by pressing stop. So here's how I initially set it up. I had just the mid-level switch. Once the level goes up, this will close and latch the mixer on. And I made it so that the mixer will unlatch when either the level goes back below there, or if you click stop. But I found there was a bit of an issue with this actually. See, it works fine. You see, if you fill up the tank and this switch gets passed, the mixer latches and turns on here. And it works when you discharge it as well. See the level going down, and the mixer turns off. However, the issue I found is that if you fill up the level above the mixer, turn on the mixer and click stop, the mixer doesn't actually turn off because this mid-level switch is still latching the mixer on. So we need to figure out a way to get around this. So here's what I did to fix this problem. I made a new Boolean variable. I decided to name it mix control. And here's how I decided to implement it. So I made it so that if you click stop, then you will latch this variable, mix control, and I will actually put this variable in series with the mixer. And I'll make it normally closed. That way when you click stop, you energize this coil and it will actually open up, meaning the mixer will turn off. Now to turn the mixer back on, when you resume, I figured, well, to resume the operation, you're either going to press push button 1 or you're going to be pressing push button 2. And you could simply have either of those buttons on latch the mix control. And this way, the mixer will be able to operate depending on the level of the tank. So let's just see if it works. Here we go. We're going to go fill it up. And remember before, when we filled it up and clicked stop, the mixer wouldn't actually turn off. But now that we have this mix control, when we click stop, it's going to latch this and switch this variable to a 0 and turn off the mixer. So you can see the mixer stops. And to unlatch the mix control bit, we're just going to drain the tank a bit, and you can see the mixer turns back on. So yeah, that was a fun one. I guess we'll just go on to the next. Okay, so now we're on the XOR, number 24. Design a program to perform exclusive OR logic. Pressing PB1 should energize lamp 1. Pressing PB2 should energize lamp 1. Pressing both PB1 and PB2 should not energize lamp 1. Okay, so before we do this, I'm just going to give you guys a little introduction to the exclusive OR logic. So here I've prepared this little document for the exclusive OR logic, also known as XOR. So as with any logic, truth table is important. It tells you what the output will be based on all the possible combinations of inputs. Since we have 2 inputs, that means we have 2 to the 2 outputs because it's binary, which means we have 4 possible combinations leading to potentially 4 different outputs. And this is how the truth table looks for an XOR gate. You can see when the inputs are 0 and 0, or 1 and 1, you get a 0. But when the inputs are 0 and 1, or 1 and 0, you get a 1 on the output. And so an XOR gate can also be known as a difference detector. It will output a 1 if its Boolean inputs are not the same. And will output a 0 if its Boolean inputs are the same. And it turns out in Boolean algebra there's actually an expression to represent this logic here, and that's what we're going to use to make our ladder logic. So it's x, which is the output, is equal to a bar b, which just means not a multiplied by b, plus, which is or, a b bar, so a multiplied by not b. Now let's give this a shot here. So if we call input 1 a and input 2 b and make the output x and apply our formula here, we'll see what is a bar b. In this case, that would be not a, which would be 1, multiplied by b, which would be 0. Obviously, anything multiplied by 0 is 0, so this term would be equal to 0. When I want a b bar, that would be a multiplied by not b, so 0 multiplied by 1, 0. So we have 0 plus 0 equals 0. Okay, for this scenario, a bar b. What is a bar? That's not a, that's 1. What is 1 times 1? Is 1. So our first term is 1, and in Boolean algebra, 1 plus anything is equal to 1, so we don't even have to solve this second part. Now let's go on to this scenario. A bar b, so not a, that would be 0, multiplied by b. 0 multiplied by 0 is 0, plus a b bar, so 1 multiplied by not 0, so 1 multiplied by 1. So 0 plus 1 gets you 1. For this last case, a bar b, so not a is 0, multiplied by 1 is 0, plus a b bar, so 1 multiplied by not 1. So 1 multiplied by 0 gets you 0. And there you have it. That's the XOR gate. Now let's use this information to finish our ladder logic. Okay, so here's the logic based on what we just went over. And yeah, I'll explain to you what we're looking at. So this first branch represents a bar b, the first part of our expression. The normally closed contact represents the NOT function. So PB1 normally closed would be a bar. PB2 normally open would be b. And the fact that they're in series is indicative of the multiplication in the Boolean algebra, which is the AND function. Because in order for the signal to get through, it has to pass through this and this contact. And on the other branch, we have a b bar. So in order for the signal to get through, it has to pass through a and b bar. And both of these branches are in parallel. That is what the addition symbol represents in the expression that we made, which is representative of the OR function, because the signal only has to go through one branch or the other in order to trigger the output. So that's how we came to this logic based on Boolean algebra. Now let's see if it works. And if you remember, the exclusive OR gate was a difference detector. So see here, both the inputs are the same, they're both off, and the output is off. So that's what we expect. We'll turn them both on and see the output will turn off as well. Now if we just have push button 1 energized, you can see that the output will be on. And on the flip side, if we just have push button 2, you can see the output is also on. So there you have it, XOR gate. Okay, so the next one that we have to tackle is stack light number 3. However, I don't think we'll have time to go through all of this in this video, so we'll just save it for the next one. Yeah, so that's going to do it for today. Thank you for watching. I hope you learned something and had some fun. Yeah, please smash like, subscribe, and yeah, check out the website PLC IOSIM. Yeah, kudos to whoever made this. Anyways, thanks.